Okay, so let's start our morning session. So our first speaker today is Professor Mohamed Elhamdadi from University of South Florida. His title is Circular Orderability of Quandles. So let's welcome.
Oh, thank you. First of all, I would like to thank the organizers for the invitation. And I thank all of you guys. The plan is basically to talk about this, this notion of circular orderability put on Quandle. Now, in groups, this is well defined. People have been studying it for a while. And as you know, there is a lot of work happening on Quandles. And basically what I will talk about is recalling a little bit of orderability of groups, then circular orderability of groups also, and show that there is already orderability of Quandles. This was introduced by Bardakov, Pasi, and Singh in a recent paper. And we will introduce the circular orderability, and we will show the difference between two notions. In general, orderability implies circular orderability, but not the other way. Oops, sorry, maybe just, okay. I quickly review Quandle since we already heard talks about Quandle. This is just the definition. Set with binary operation satisfying these three axioms. And the only two examples I will use mostly is these two Quandles made from groups. The first one is conjugation, and the second one is the core Quandle. Okay, let me review a little bit of orderability on groups. This is well studied for a long time ago. I recall the definition of a group is called right orderable if there exists a strict total ordering on it, which satisfy that is invariant from the right. Then G less than H implies GF less than HF. Similarly, you can define left orderability. The same thing, just multiply from the left. Now in groups, which is completely different than, as you know, than Quandles, in groups, anytime you have left ordering, you can create right ordering from it, and vice versa. If you have right ordering, you can get left ordering. Basically, because there is a unit element in groups, while in Quandle we don't have such elements. And thus there is one-to-one correspondence between left ordering and right ordering on group. If X is less than Y, we define the less prime by this definition, Y inverse less than X inverse. And we consider the set of right ordering on group. We denote it by RO of G, just right ordering on group. Oh, sorry, I'm having trouble. I'm sorry, just one moment. I'm having trouble using this. Okay. I need to get rid of, okay. This is so sensitive, I'm sorry. Okay, a group in which a group is called bi-orderable if there is an order that is left order and right order at the same time. Now here are some examples. As everyone knows, the real line with addition is right orderable. It's also left orderable. If you take real numbers minus the 0, it cannot be right orderable. Basically because there is a torsion element in it. -1 has torsion, and that gives contradiction. Abelian groups are bi-orderable if and only if they are torsion-free. There is also Patrick Duhornoy's ordering on braids. This is a little bit technical, but this is really good work on ordering of braid groups. And he defined a word, W is called sigma I positive, meaning greater than 1, if it can be written in the form W equal alpha naught sigma I alpha 1, with the condition that alpha 0 and alpha I do not involve any generators less than I. No sigma j in which j is less than I. In other words, alpha 0 and alpha 1 are just words in sigma I plus 1, obviously, or its inverse, up to sigma n minus 1. Here is a small example. Take sigma 1 is less than sigma 2 sigma 1 according to this definition. Now, obviously, you multiply by sigma inverse from the left, you'll get sigma 1 inverse sigma 2 sigma 1. But according to Duhornoy's definition, that is not less than, that is not greater than 1. What you have to do is you basically have to change sigma 1 inverse sigma 2 sigma 1 to sigma 2 sigma 1 sigma 2 inverse. And as you can tell, sigma 2 sigma 1 sigma 2 inverse is sigma 1 positive, greater than 1. Now, the braid group is not bi-orderable, but the pure braid group, Pn, is bi-orderable. Now we consider the group of homeomorphism preserving the orientation of the real line, then order preserving maps, and that group is left orderable. You can see that the order on it is defined in the following. Take F and G not equal. Now the real line is orderable. You pick the first element where they are distinct. And then you, by definition, you say that F is less than G if and only if F of Xi is less than Gi. And we have this theorem which says that a group G is a countable group G is left orderable if and only if it embeds into homeoplus of the real line. Now we will see similar theorem for changing basically left orderability by left circular orderability. In that case, the real line will change to the circle. Here are a few examples. Let's H be a normal subgroup of G, and let's take the quotient of it. If H is orderable and K is orderable, then you have an order denoted by less H in H and K. If they are right orderable, then one can construct an order on G in such way that G is right orderable. Then basically, if the normal subgroup is orderable, basically I say right orderable, but everything can be done for left orderable. And I just always focus on one of them without paying attention to the other one. As example, we can use this theorem to show that the fundamental group of the Klein bottle is right orderable. Now, the fundamental group is written by these two generators with the relation xy x inverse equal x inverse. Then it's clear that if one take the subgroup generated by x, which will play the role of H in this theorem, and the quotients will be played by the subgroup generated by Y. And those are infinite cyclic, they are orderable, then the fundamental group of the Klein bottle is orderable. The theorem of Jim Hoey stated that knot groups are left orderable. Then if you take fundamental group of knots, you get orderable group. His paper is titled on locally indicable groups. In fact, there is a notion of indicable group which imply left orderable, but it's too technical and we don't need it here. Now, if you have a group G that is bi-orderable, this is really interesting, that if an element commute with any power, if X commute with any power of Y, it has to commute with X. And the proof is not difficult. You just prove by contradiction. You assume that XY is not equal YX, since its total order one is smaller than the other one. And by induction, you just multiply from right, left, and using the fact that XYN equal YNX, you can end up with contradiction. Now this, we can use this to see that as consequence, the fundamental group of the torus knot TMN cannot be bi-orderable. Then from the fundamental group of the torus knot, you just consider X equals, say, B. B commute with A to the power M, because A to the power M is just Bn. And if it was bi-orderable, it will imply that A and B commute, and that is not right. That is not correct. The fundamental group of the figure 8 knot is bi-orderable. Now, Tararin defined this, studied this orderable group. In fact, the question is, if you take the set of left orderable on group, set of left orders on group, you want to know it's finite or infinite, and what kind of infinity, if it is infinite. Now the paper is titled "On Group Having a Finite Number of Right Orders." It's in 1991, and he gave a complete classification of all groups G with only finitely many left orders. Now, nowadays they are called Tararin groups. Now, his theorem states that you will have finitely many left orderings on a group G if and only if G admits a rational series. Then you have G, which is T0, and then you have the series with this condition, that for any I between 0 and m-2, there exists an element of Ti quotient by Ti plus 1, whose action by conjugation on Ti plus 1 quotient by Ti plus 2 is by multiplication by negative rational number. Let's look at some examples. For example, the set of ordering has cardinality 2 if and only if G is torsion-free abelian of rank 1. And if you have a group G containing a free abelian normal subgroup of rank at least 2, such that the quotient is right orderable, then G has uncountably many different right orders on it. Peter Linnell later used Tararin's work to prove the following theorem. It's in 2011. He proved that the space of ordering on here we consider right orders, cannot be infinitely countable. In other words, it's either finite or uncountable. And here we saw the example in which the first example was cardinality 2. Okay. Now we move on to quandles, and we consider the notion of orderability on quandles. Now, this was defined first in paper by Bardakov, Pasi, and Singh. The title of the paper is Zero Divisors and Idempotent in Quandle Rings, appearing in Osaka Journal. Now, the definition is natural. You have a quandle, you have a binary operation on it. You add a strict total ordering on it, and you want it to be right invariant. S is less than T implies that S star R is less than T star R for for any element RST in the quandle. Similarly, you can consider left orderable just multiplying from the left. Now they proved among the results, they proved, for example, that the conjugation of a group is the right orderable quandle, but not left orderable quandle. While the core quandle, if you take a group and you consider the core quandle, remember the conjugation, the binary operation is x star y equal y x inverse y. It is left orderable, but not right orderable. Now, naturally, one can talk about homomorphism and isomorphisms of orderable quandles. Naturally, you just take a map that preserves the quandle operations and this preserves the ordering. Then a few years ago, we studied the topological quandles on the real line. It's basically take the real line with the operation on it, x star y equal alpha x plus 1 minus alpha y. Now, topological quandle means you require that the right multiplication is homeomorphism. You still have idempotency. The only difference is that your space is not just, the quandle is topological space, and the binary operation should be continuous. The right multiplication is homeomorphism, and you have right distributivity. Then if alpha is positive, then the real line, this quandle is right orderable. If alpha is less than 1, it is left orderable. And obviously, if you want it to be bi-orderable, then alpha is between 0 and 1. In fact, in this paper, we classified topological Alexander quandles on the real line. And the result was that if alpha and beta are distinct, then the two topological quandles will be distinct. Recently, there was a paper, this is 2021, by Randall, Hitesh, Mahendra Singh, and Manpreet Singh about orderability of linked quandles. And here we can recall few results from this paper. First, I recall the definition of enveloping group of quandle. Start with the quandle. Consider the free f of q, the free group on it, and then quotients by the normal subgroup in which you force the binary operation x star y to become conjugation. That is x star y equal y inverse xy. And they proved if naturally q this inside the enveloping, you can map Q into this enveloping group. If the mapping is injective, then if the enveloping group of the quandle is bi-orderable group, then the quandle is the right orderable quandle. If you have a knot K and the fundamental group of it is bi-orderable group, then the fundamental quandle of the knot K is the right orderable quandle. They also, they also studied the orderability of the fundamental quandle of torus knots, and they showed that the fundamental quandle of the torus knot TPQ is not right orderable. Now, they showed also that for the threefold, the fundamental quandle is neither right orderable nor left orderable. Okay, now we can start talking about the notion of circular orderability. We will see in a moment that orderability implies circular orderability, but not the other way. Now, if you have a set T you define, we say that there is a circular ordering on it. If there exists a map, C going from the Cartesian products of T, 3 copies of T into the set -1, 0, 1, with the following 2 conditions. That if you pick 3 elements, T1, T2, T3, if any 2 of them are equal, the map C will have value 0. And this if and only if, then C of T1, T2, T3 is 0. If and only if they are not pairwise disjoint. The set T1, T2, T3 are not all distinct. And there is this other condition, which look like a co-cycle condition. If you have four elements in the set, call them T1, T2, T3, T4, then as we do in singular, basically you remove 1 and you alternate the sign, plus, minus, plus, minus. Then I remove T4, I get C of T1, T2, T3, minus, now I remove T3, I get T1, T2, T4, and then you remove T2, you end up with C of T1, T3, T4. It's like in singular homology. Okay, then this is the definition of circular ordering on any set. Now, in a moment, we'll make it on a group, and then later we'll talk about circular orderability on quandle. Now, this is the definition to remember for circular ordering on the set. Then the map will have value 0 if and only if 2 among the 3 elements are equal. And then this condition we will use later in. Now, there is a notion of circular orderability of groups. Now, obviously, you can talk about left and right. If it's left invariant, you'll call it left circular orderable. If it's right invariant, you'll call it right circular orderable. Then a group G is right circularly orderable if there exists a circular ordering, a map C from G cubed to the set -1, 0, 1, satisfying the previous 2 conditions, and the invariance from the right. Then again, the conditions are this, basically this co-cycle condition, and the map is value 0 if and only if 2 elements are equal.
Excuse me.
Yes.
Yeah, Mohammad. So how does the orderability imply circular orderability?
I will talk about it. It's just yes. It's basically the idea is this. I define C of. I think I have it in one of the. Let me see if I have it. Yeah, here it is. It's coming. Okay.
Okay. Thank you.
Yes. Okay. Let's see. Okay. Then this is the definition of right circular orderability. Okay. Here are some examples. The cyclic group Zn is right cyclically orderable. Sorry, I have problems saying the word circular ordering or orderable. In fact, Idris Ba and Adam Clay proved the following, that you will have a finite, the set of rights RCO of G stands for the set of right circular ordering on G. That set is finite if and only if G is either isomorphic to the cyclic group Zn, or G is isomorphic to the semi-direct product of Tararine group with the cyclic group Zn. Now, obviously, I'm not doing any proofs here. I'm skipping all the technicalities. This is just to give an idea of what's going on. And then, obviously, one can look at the details in the specific papers. Now, remember, we have this theorem that G is countable and left circular orderable group if and only if it embeds into homeoplus of the circle S1. This is the analogous to the previous result. We saw that a group G is countable left orderable if and only if it embeds into homeoplus of the real line. Now, you see that circular orderability is related to the circle, obviously, and the cyclic group. Okay, now we give the definition of quandle being right having right circular ordering. Then a quandle is right circularly orderable if there exists a circular ordering C, meaning a map from the Cartesian product of Q with itself 3 times into the set minus 1, 0, 1. And we will require that it's invariant by the quandle operation from the right. Now, the left, you can define the same thing. You just assume it's invariant from the left. This is now orderability implies circular orderability, and this is just the proof is constructive. If starts from a quandle that is orderable, okay, and construct the map in this way. You see that we set the map the value of C equal 1 if S1 less than S2 less than S3 in circular way. Just imagine a circle and you put the three variables on it, S1, S2, S3, and you get one direction, say clockwise, S1 less than S2 less than S3, or S2 less than S3 less than S1, or S3. And in the other direction, counterclockwise, it's -1. And if 2 elements are equal, this is going to be 0. And one can check, one can do the details that this map does the job and gives circular orderable quandle. Now, the two notions are different. We will see examples for which this is also true for groups. Orderability implies circular orderability and not the other way. We have this proposition. Now, obviously, we looked at the conjugation quandle and the core quandle. Okay, then let's GC be circularly orderable group such that C is both left and right invariant. Then the conjugation quandle is right circularly orderable. This is exactly similar to the proof in the previous paper I mentioned of Mahendra Singh, Manpreet Singh, and the third author. Sorry, I forgot the name. Okay, then this is just, the proof is just straightforward. Now you see that in conjugation you have G you have the G from the right and you have the G inverse from the left. That's why you require left and right the map to be invariant from the right and from the left. Are there any questions so far? Okay. Bicircular orderability of groups have been studied since the 1950s. In 1959, Sierczewski, I'm sorry I can't say the name properly, the paper is on cyclically ordered group, published in the Fundamenta Mathematica in 1959. He gave complete classification of this type of groups. And the theorem states the following. If a group G is bicircularly orderable, then there exists bi-orderable group gamma, such that G is a subgroup of gamma cross S1, the product of gamma with S1. Moreover, the bicircular order on G is determined by the natural bicircular order on gamma cross S1. Now, as I mentioned earlier, orderability implies circular orderability. By the natural bicircular order, it is meant that if you equip gamma across S1 with the lexicographic bicircular ordering, then the bicircular ordering on G is just a restriction of this lexicographic circular ordering on gamma across S1 to the subgroup G. One can get a classification of all the subgroups, and hence by Sierczewski theorem, gives infinitely many examples of bicircularly orderable groups that are not bi-orderable. Let H be a bicircularly orderable group, then conjugation of H is right orderable. Then the proof is not difficult at all. Let H be any bi-orderable group. Consider the conjugation of H. Then it is right orderable because the group is orderable. Then the quandle, which is conjugation of H cross S1, which will be the product of the quandle conjugation H with conjugation S1, but S1 is obviously abelian, then conjugation will be trivial. And then using this proposition 4.4 from the paper of Randall, Mahendra Singh, and Manpreet Singh, orderability of quandles. That's how we get these results. And then the result follows automatically from Swiatkowski's theorem. We have the following lemma. If G is non-trivial group with at least 3 elements, then the quandle conjugation of G is not left circularly orderable. Then the proof goes like this. Let G be any non-trivial group with at least 3 elements. Consider the conjugation quandle, and then assume a contradiction that you have a map C, which is left circular or ordering. Now you take C of the S1, S2, S3, and you multiply it by the you start by E, the identity element in the group from the left. That turns it into 0 because you end up with 3 equal the identity element. Then the function is constant 0 map, and then it implies that conjugation cannot be left circularly orderable, because then you will have 3 elements that are pairwise disjoint, but the value of the map will be 0, which will contradict the definition of circular ordering on the quandle. Now, circular orderability of quandle is different than orderability of quandles. Here are some elementary examples. The trivial quandle with 2 elements is bicircularly orderable. Since the trivial circular ordering, we just take the map 0. And it is both left invariant and right invariant. Since this quandle is not left orderable, trivial quandles are never left orderable. This shows that the 2 notions are distinct. Now we looked at a few small quandles. Obviously, there is a lot to be worked on this for this notion. Here is the 3-element quandle with the orbit 1, 2, and the other orbits singleton 3. Now this quandle is neither left nor right circular orderable. The proof is elementary. It's really just start with C of x, y, z, multiply by 3 from the right. Okay, 3 is 1 orbit, then this end up to be 0. And then the quandle can't have left or circular ordering. Now, if you assume that C is right invariant, then here we will need to use the co-cycle condition. Start with C of 1, 2, 3, multiply by 3 from the right. You get C of 1, 2, 3 equals C of 2, 1, 3. Now use the co-cycle condition. This C, pick the 4 elements 1, 2, 1, 3. And then each time remove 1 element and alternate plus, minus, minus. You see that you have C of 1, 1, comma 3, that will become 0. The first part C of 1, 2, 1 will become 0, and then you will obtain that C of 1, 2, 3 equal minus C of 2, 1, 3. And then you get contradiction. Then this small, very small quandle of 3 elements, it's neither left nor right circularly orderable. Now, obviously, one can look at the dihedral quandle of 3 elements. This quandle is a little bit different than the others. It's commutative quandle, x star y equal y star x. That's why I wrote it as 2x plus 2y instead of 2y minus x, the traditional one. It's neither left nor right circularly orderable. And again, the proof is not difficult. If at least 2 of the 3 elements are equal, by definition, the map C has value 0. Now we focus on the 3 elements being distinct, pairwise distinct. And we know that in this quandle, the product of 2 gives the third one. Then if C of xy, xyz, one again, I call the element just xyz, 3 distinct elements. Now, if you multiply, sorry, if you multiply by x from the right, then you prove that C of xyz is the same thing as C of xzy. Similarly, I multiply by y from the right, you get C of xyz equals C of zyx. And similarly, you obtain the fact that C of xyz equals C of xzy, this equality, which means that any permutation of those 3 elements will leave the value of the map C of xyz unchanged. But since C is a circular ordering, it satisfies this condition. C of xyx, again, I take xy, xz, and remove 1 element and alternate the signs, plus, minus. The sum is 0, and then one gets contradiction. Now, C of x, xz is 0. C of, similar to the previous one, C of xy, x is 0, and then you get contradiction. Then these are some small examples of small quandles that are neither left nor right circular but orderable. Now we're going to look at the space of ordering on quandles. But before we do that, obviously we start from group. Then in 2004, Adam Sikora introduced for any group a topology on the set of right ordering on G, and he proved the following theorem. In fact, he proved it even for semi-groups. If G is semi-group, then the set of right ordering of G is compact topological space that is totally disconnected. Totally disconnected means just the connected components are singleton. And he proves that if G is Zn, the space of right ordering is homeomorphic to the Cantor set. Now later, this result was generalized by Yusef Prichitsky and Dabrowski and Harizanov and Viv, and they proved it for general magma. That's magma is just set with the binary operation that is closed. And if X star is a magma, then the set of right ordering on X is compact topological space. This was in 2007. Now we look at the set of right circular ordering on a quandle. And let's start with the quandle Q. We denote RO of Q, the set of right ordering on Q, and RCO mean right circular ordering on the set of right circular ordering. Then, as we mentioned earlier, right ordering gives a right circular ordering. Then the set RO is subset of RCO. Now we consider a topology on the set of right circular ordering of a quandle Q. I recall the definition of Tikhonov. A space is called Tikhonov. I think it's called also completely regular space if you can basically separate points from closed subset that does not contain it. It's similar to Urysohn lemma. If you have a continuous map, I think this will be little f from x to the interval 0, 1, which map x to 1, and the closed set A of x into 0. And now consider the set of right circular ordering on Q. It's just maps. We denoted earlier the maps from Q3 to the set -1, 0, 1 with Tikhonov topology. And then we define the following. Now, this little bit some technicalities, but it's not difficult. Then if x equal y, if two of them are equal, we denote gamma of Q, that's the set of those elements. The lemma is that the set of this right S, where S belongs to Q3 minus, we remove the element where two of them are equal. We prove that this is sub-basis for the topology on the right on the set of right circular ordering on Q. Now we define this set V sub S -1, just the maps which send the element into -1, the 0 which map them to 0, and the other one maps them to 1. And this form a sub-basis of this Cantor set of maps from Q3 into the set -1, 0, 1. Sorry. Now, since it's maybe a little bit technical, I can go through it. If we take the intersection, one has to have the other, VS0 is just the maps which send this to 0. And then the intersection is just, this is subset, the intersection is just RCO. We do the same thing with the left. In fact, here I'm talking about the right, but one can do the same thing for the left. And then we have this theorem. Basically, we want to show in similar ways to the case of group that if Q is a quandle, the set of right ordering on the quandle is compact topological space. The idea is just we prove that the set of right circular ordering. Here I have a typo. We prove that the set of right circular ordering on Q is closed into the space of maps from Q3 to the set -1, 0, 1, and thus we obtain compactness. Here are a little bit the details. Then an element C is a map. It satisfies it's equal 0 if and only if two of the three elements T1, T2, 3 are 0. The co-cycle condition and the right invariance. Now we consider the set A, which is the maps, such that it's C of T1, T2, T3 is 0. And then we write it as intersections of VS0, where S is in gamma or in the complement. And similarly, and we prove the theorem. Now, the topology on R of Q is constructed by choosing a sub-basis of this collection. Then delta is the diagonal, and V sub AB is a set of ordering such that A is smaller than B. Now we prove that the set of ordering embeds into the set of circular ordering, precisely that the inclusion of the inclusion map sending RO of Q into RC of Q is an embedding. The proof goes like this. Then we have the sub-basis as we mentioned earlier. And then we just take the pre-image, and that's straightforward. Then the injective map G is continuous, and the RO of Q is compact, and the Cantor set is Hausdorff. Then the map G gives an embedding. I will end up with these questions. We looked a little bit at the fundamental quandle, circular orderability of fundamental quandles, but we have some smaller results, but nothing that's very interesting. That's why I'm not talking about it. I end up with these few questions. Can RO of Q and RCO of Q be homeomorphic? That's first question. We don't know a case when the set of right circular ordering of the quandle is finite. It will be nice to have an example of that. And also find another characterization of right circular orderability. Now for groups, this is well studied, but for quandles, it will be interesting to have some other characterization. And obviously, the other question is right circular ordering on fundamental quandle of knots. Okay, here are a few references. There is a nice paper by Etienne Gis, but unfortunately, I think it's in French group. Now, this one is in a group acting on the circle. This one is good. And the paper of Randall, Singh, and Singh, which is a nice paper. Sikora's paper is also a nice one, topology on the space of ordering of groups. And the last two papers. Okay, I stop here. Thank you so much. If you have any question and any comments, it will be appreciated.
So any questions?
Yeah, can I ask a question?
Sure.
Yeah, so Mohamed, so the definition of circular orderability seems like, as you related, the singular complex situation. So why only we take the 3-4 product? One could have higher order, maybe higher orders circular orderability.
Absolutely,
I mean,
absolutely.
Same definition.
Yes. To be honest with you, I'm not expert on right circularity of groups. I just studied them a little bit, but yes, absolutely. Your question makes sense. Yes.
Because instead of removing double diagonals, so we remove triple diagonals, like in the definition, and perhaps there is a way anyway. Yeah.
Absolutely. Yes. That's a nice question. That is a really nice question. Yeah.
Thank you.
Oh, my pleasure. Yeah.
So any other questions? So okay, let's thank Mohamed again.
Well,